Hi everyone, my name is Steve Kubrak and I am a program manager at a Fortune 5 company. We've been doing AI for a little while at the company and I've been studying AI for a long time. And I needed to get a certificate to prove to everybody that I actually knew what I was talking about. That's why I enrolled in this course. So this is my presentation for predicting the electrical energy output of a combined cycle power plant. This project aims to predict power efficiency of a combined cycle power plant using various machine learning regression models. The objectives are to identify significant features and develop a predictive model with high accuracy. The data set includes 4 features related to power efficiency to be included in the model. They are temperature, ambient pressure, relative humidity, and exhaust vacuum. So setting up the model. This is a regression problem. It's fairly easy when you look at the data. I selected mean squared error to use as my evaluation metric as it's the most common and it's the easiest to understand. I used a linear regression algorithm for these models, but random forest regression could work and gradient boosting regression could have worked as well, but I wanted to pick one of the 3. The models were built using different combinations of features to the best predictive performance using the same algorithm. And this way I can have one algorithm for the 3 of them and compare them together as opposed to getting more esoteric math on it. The combinations of the features are as follows. I used all 4 features for the standard for the control. I used temperature and relative humidity versus power, and then ambient pressure and exhaust vacuum versus power as well. So temperature and relative humidity and pressure and exhaust vacuum are the models I selected and compared using a validation set. And the validation set was based on the test data that I spooled off. The final model, temperature versus relative humidity, was selected based on its R² value and its mean squared error. I used Excel manually, so I had to cut them off. The test set was about 1,914 items, and the 80% was the rest. And I compared them with cross-validation. So my results and interpretation. So in the plots below, which you see in a minute, our temperature and pressure and vacuum all showed positive relationships to PE, while relative humidity showed a negative relationship. The regression output that showed the most significant, like which model was is the best one to do the interpretation, was the temperature versus relative humidity and power. The output had the most significant R² value. So remember, R² values, the closer you get to 1, the better. And for mean squared errors, the lower you get to 0, the better. And these are what came out of that model. The key metrics are, for R², it's 0.9287, and for mean squared, it's 21.7. Here is our data that comes out. This is the final model up here. This was all done in Excel. And thank you, Excel. And then the second one, I predicted the mean square error down there on the bottom. That was also Excel, but I was putting it through the website. These are just plots for it, right? This is my actual versus my predicted, right? Which you can see the linear regression right here. I mean, it didn't draw the line, but obviously there's a line that goes through. And the plot of the squared error over the data points, right? These are the average errors. This is the squared error, which is a nice correlation. So what that does is the final model, in conclusion of all of this, right? The final model, which is the temperature and relative humidity versus power, showed a strong predictive performance with an R² value of 0.9287. This indicates that the model explains approximately 92.87% of the variance in power efficiency. The other model, which was the pressure and vacuum versus power, was 0.8734 or 78.34%. So that was worse than the first one. Remember, the closer R² is to 1, the better. And the explanation, since R² equals 1 would mean it predicts 100% of the variance. So the closer you get to 1, the closer you get to 100%. Also, the mean squared error of 21.7 is fairly low, and so just a good fit for the data. The coefficients for these variables suggest a substantial impact on power efficiency. Basically what it tells, in English, the higher the relative humidity, the less power you get out of it. And all the other ones were the other way around. The higher the temperature, the more power you get. It just like humidity just like makes all this more complicated. And I would presume it's our friend Pivner and all that other good gas stuff. So therefore, managing indoor temperature and humidity levels more effectively could lead to a boost in energy savings. So although the current model has a high R² value, there may still be room for improvement. Right, exploring more advanced data models and learning algorithms, the other regressions, the other models I could have used for that, or just using more models at once, including other features that weren't currently in the data set, things like time of day, occupants in the building, cycle power, all that kind of stuff, could potentially capture more variance and improve predictive accuracy. Remember, more data is always good. That's the whole point of statistics. And that is my presentation.